Okay, so this week we are at 4:20, so we're nearing the end of the semester. So the lectures are going to be molecular shape and intermolecular forces. So that's the end of chapter 10, and then there's also section 12.6. So this is kind of most of beyond chapter 10 is in Chem 102, but I do go over this because I think it's important and relevant to what we're doing now. So this week there's no homework because we're basically learning about molecular shape, and the lab goes over this, and it's a fairly involved lab, so I didn't think it was necessary to have homework as well, and 2 quizzes. So there's nothing to turn in this week because last week, since we had the exam, there wasn't any new assignments. So as usual, I'll go over the lab, how to do the lab on Wednesday morning. So I recommend that you watch the lectures first and read first because in this lab, it's particularly important to read about it first, or it's going to be hard to understand. And I think there was something else I was going to say about that, but I can't remember, but we can come back to it later if I do, or I'll just send a announcement. Okay, so basically what I'm going to do today is I'm going to go over exam 2, and I'm also going to go over project 2, which you can do for extra credit. So I guess let's get started first of all with the exam. All right, so started. Okay, so question 1, which of the following statements about chemical formulas is true? And I have to read through these. Okay, the subscripts represent the relative number of each type of atom in the compound. So that sounds right, but let's just read the rest. The subscripts represent the relative mass of each type of atom in a compound. So it's not mass, it's number, so that would be incorrect. The subscript may vary depending on how much of each element is very available, and that is not true because by definition, a chemical compound, which is indicated by a formula, has an exact number. It's always going to be the same. And the subscript represents the charge, and that is also not true. You can figure out the charge, but it does not directly represent the charge. So what is the formula mass of H2O or water? So for this, you need your periodic table, but I'll just go, I won't open my table for this, but if you look at your table, if you have it handy, oxygen has a mass of 16 and hydrogen has a mass of 1. Since there's 2 hydrogens, that's 2 total. So that's 1 plus 1 plus 16 is 18. So that would be the second choice. Question 3, based on the following diagram, which electromagnetic radiation listed below is the most energetic? So the shorter the wavelength, the more energetic. So if we look at the possible choices, radio waves it's got very long wavelengths, so that's the least energetic. Microwave is just a little bit shorter than radio waves, but it's still a pretty long wavelength, so that's not going to be the answer. We have X-rays and visible. Now, visible is right in the middle. X-ray rays are quite short. They're not the shortest. That's gamma rays, but that wasn't an option, so the correct answer is X-ray. Question 4, higher energy electromagnetic radiation has, and so basically, again, thinking, I'll just move back down to this thing because this kind of tells you the answer if you look at the number above. So if it's, or at least kind of, you can look at the wavelength. So basically, higher energy electromagnetic radiation, again, it has a shorter wavelength. So we're looking at the answer. We know it's a shorter wavelength. It's not a longer wavelength. So that's eliminates the second and fourth answer. So we have a shorter wavelength, and then there's lower frequency, but actually there's an inverse relationship. So when we have a shorter wavelength, frequency is the amount of waves that pass a certain point, and all at a given time, in a given amount of time, and all electromagnetic radiation travels at the same speed. So that means if we have a shorter wavelength, the waves are closer together, like over here, and then it's going to have a higher frequency. So more waves are going to pass a point in a given amount of time. So that would be choice number 3 here. And then we have, which of the following statements about electromagnetic radiation is true? And again, I'll just read them all and we'll see which one makes most sense. EM is a type of energy that results from oscillations in electric and magnetic fields. And that is true, but let's just look at the next one. EM behaves as both a particle and a wave. That's also seems to be true. EM is not a form of matter. That's true. It's like, it's one of 2 components, major components of our universe. Matter is one component and energy is another. So an electromagnetic energy is a form of energy. So it's not a form of matter. And EM has no mass, and that is true too. Matter has mass, but energy does not. So in this case, all of the statements are true. The distance between adjacent wave crests is called, and the answer to this is wavelength. That's the definition of it. It's not trow. That would be like the deep part of a wave. Frequency is the amount of waves that pass a point in a given amount of time. And I'm not even sure what that is. So it's wavelength. All right. When an electrical current is passed through neon and the resulting light is passed through a prism, what is observed? So I don't know why these lines are appearing. When we have electrical current pass through neon and we have a prism, that was what we did in, I can't remember what lab number it was, but we saw that. We have discrete lines of different color. Hopefully remember those discrete lines. So it's not white light, it's not a continuous spectrum. There's discrete bands that result from electrons falling down to ground state. What happens to an atom when it absorbs energy? The atom, okay, and let's again just look at the choices. The atom re-emits the energy as electromagnetic radiation. So that sounds correct, but let's read the others. The atom re-emits the energy as heat. That is not correct. It's electromagnetic radiation is what is released. The atom stores the energy, and that is not true. So as soon as it absorbs energy, it's going to re-release it because it wants to be in ground state. So it's a very rapid process. And the extra energy increases the speed of electrons in their orbitals. And this sounds like it might be something that might happen, but that's not the case. What happens is basically the electron is bumped up to a higher orbital. It has nothing to do with the speed of the electrons. So that would be the top choice here. Okay, according to the wave mechanical model, which of the following statements describes electron arrangement? A, electrons prefer to be in the lowest energy state possible. B, mathematically, so I'll just like say, that sounds correct, because they do prefer, like basically everything prefers to be in the lowest ground state lowest state possible. So that's why water falls down waterfalls, or ball rolls downhill, because it would prefer to be in the lowest energy state possible. Same is true for electrons. A mathematically defined space in which electrons reside is called an orbital, and that's true. That's a definition that you hopefully know by now. an electron cloud can be used to show the likely distribution of atoms, and that's also true. So that within an orbital is like a space, but within that space, the electron can be anywhere in that space. So imagine like the s orbital is like a sphere. The electron can exist anywhere in that sphere, and it's more likely to be in some parts of the sphere than others, but it could be anywhere in that sphere. So all of these statements are true. When filling orbitals of equal energy, electrons fill them singly first with parallel spins. So this is a rule that we learned about. It's not ground state, that's the lowest energy. It's not Hund's rule. That's like a similar, it's also a rule about electron filling, but that has to do with if they're filling more than one orbital. So it's the Pauli exclusion principle. Or wait, no, I'm sorry, it is Hund's rule. I have to reread this. It's hard to talk and like, so it's a fill singly first, with parallel spins. So that's Hund's rule. The Pauli exclusion principle is where they have the up and down arrows. So they have opposite spins in the same orbital. When they're filling, when there's more than one orbital in a subshell, they fill singly first and they have the same spin. So, but within an orbital, they have to have opposite spins. And Bohr's model is just a model of an atom. It's not a rule, so that wouldn't be an answer. Okay, how many electrons can exist in an orbital? The answer to that's 2, and that's true no matter what orbital we're talking about, no matter what shell, no matter what subshell, it's always can hold 2 electrons. Okay, and the n equals blank principal shell is the lowest that may contain a d subshell. So if you remember, shell 1 has an S subshell only. Principal shell 2 has S and P, and shell 3 has S, P, and D. So that would be number 3 right here. And I should mention too, I'm not sure quite what this exam thing does. I think it scrambles the answers. So when I'm talking about this here, make sure that you're listening to what I say is the answer as opposed to like the order, because it might be different when you look at the test. But it's anyways, shell 3. How many core electrons are in a chlorine atom? So chlorine, and I think I'm going to quick open my periodic table here, which I didn't think to do before. I should have. Let's see. Because this is good to look. And for all these, you should always have your periodic table handy. Let's see. I'm trying to find right. Yeah, technical. There, that should be it. Okay, so periodic table. So chlorine is in period 3, and now I got to remember what the question is. It's the trouble with trying to open these things and remember what I'm doing. Okay, so how many core electrons are in the chlorine atom? So if we look here, chlorine has 17 electrons total, but 7 of those, it's in group 7, so 7 of those are in the valence shell, and then the remaining 10, so it's 10 of them are in the are core electrons. So you can tell by like looking at this and knowing that like the 6 for sulfur, for example, means 6 valence electrons, 7 for chlorine, or 17 is 17 electrons, but the 7 is in group 7. That indicates it's got 7 valence electrons. You just subtract to get the core electrons, or if you prefer, you could try to draw an electron configuration if that's easier for you.